Welcome to this lesson on the Debye-Hückel theory of ionic solutions. Today we're going to explore one of the most important breakthroughs in physical chemistry from the 1920s. In the early 20th century, scientists had a major problem. Their predictions for ionic solutions based on ideal solution theory were completely wrong. Ideal solution theory assumed that ions in solution behave independently, with no interactions between them. This worked well for non-electrolytes like sugar. But for ionic solutions like sodium chloride and water, measurements of activity coefficients and conductivity showed systematic deviations from the ideal predictions. The crucial observation was that these deviations were not random. They followed a very specific pattern that demanded explanation. Before we go further, let's understand what we mean by activity. What exactly were they measuring? Activity is the effective concentration of an ion in solution. It accounts for how the ion actually behaves, not just how many ions are present. Activity A equals gamma times concentration circa. Here, gamma is the activity coefficient. For ideal solutions, gamma equals 1, meaning activity equals concentration. But for real ionic solutions, gamma is less than 1. A lower activity coefficient means the ions are less effective at doing their chemical job than you would expect from their concentration alone. Enter Peter Debye and Erich Hückel. In 1923, these two brilliant physicists tackled this problem with a revolutionary new approach. Debye was already famous for his work on dipole moments and specific heats. Hückel was a talented young chemist. Together they would solve this puzzle. Let me show you the key experimental observation that Debye and Hückel focused on. Scientists had measured activity coefficients for many different salts at various concentrations. The data showed a clear trend. When they plotted the deviations from ideal behavior versus concentration, the relationship was complicated and different for each salt. Then came the brilliant insight. What if they plotted the deviations against the square root of concentration instead? When they made this plot, something remarkable happened. All the salts, regardless of their chemical identity, fell on nearly parallel straight lines at low concentrations. This was astonishing. It meant there was something universal about ionic solutions that depended on the square root of concentration, not concentration its. Now you might be wondering, why does the square root of concentration matter? What physical property of solutions depends on the square root? The answer lies in a quantity called the ionic strength. Ionic strength measures the total concentration of charges in solution. Ionic strength, I, equals 1/2 times the sum over all ions of concentration, C sub I times charge squared, Z sub I squared. For simple 1-to-1 salts, like sodium chloride, where both ions have charge plus or minus 1, the ionic strength equals the concentration. For 2-to-1 salts, like calcium chloride, the ionic strength is 3 times the concentration because of the squared charges. Debye and Hückel proposed a bold new idea to explain this square root dependence: electrostatic screening. Their central hypothesis was that each ion in solution is surrounded by an ionic atmosphere of oppositely charged ions. Imagine a positive ion at the center. On average, there will be more negative ions nearby and fewer positive ions, creating a cloud of negative charge around it. This ionic atmosphere screens or shields the central ion's electric field, reducing its effective charge as seen by other ions far away. This screening effect reduces the ion's activity, making its activity coefficient gamma less than 1. The ion is less effective because it's partially neutralized by its atmosphere. Debye and Hückel calculated how far this ionic atmosphere extends. They introduced a characteristic length scale called the Debye length. The Debye length kappa inverse equals the square root of epsilon kBt divided by 8 pi Ne squared. Here, epsilon is the dielectric constant, Kb is Boltzmann's constant, T is temperature, N is ion number density, and E is electron charge. A larger Debye length means the ionic atmosphere extends further and provides more effective screening. The crucial insight is that the Debye length is inversely proportional to the square root of the ion concentration. This is where the square root dependence comes from. Kappa inverse is proportional to 1 over the square root of concentration C. Let's calculate some actual numbers to see how big these screening effects are in real solutions. Consider 0.01 molar sodium chloride in water at 25 degrees Celsius. This is a fairly dilute solution. The ionic strength I equals 0.01 molar. Using the Debye Hückel formula with water's dielectric constant of about 80, we get a Debye length of approximately 3 nanometers. This means the ionic atmosphere around each ion extends about 3 nanometers. That's roughly 10 times the size of a water molecule. If we increase the concentration tenfold, to 0.1 molar, the Debye length drops to about 1 nanometer. Higher concentration means more effective screening. Now let's look at the mathematical result that Debye and Hückel derived. This is their famous limiting law. The log base 10 of the mean activity coefficient gamma plus minus equals negative A times the absolute value of Z plus times Z minus times the square root of ionic strength I. Here, A is a constant that depends only on temperature and the properties of the solvent. For water at 25 degrees Celsius, A equals approximately 0.51. The theoretical expression for A is 1.824 times 10 to the 6 divided by epsilon t to the 3/2 power. Z plus and Z minus are the charges of the positive and negative ions. For sodium chloride, both have magnitude 1. Notice the square root of ionic strength in the equation. This reproduces exactly the experimental observation we discussed earlier. Let's test this theory with actual experimental data and see how well it works. Consider hydrochloric acid at various concentrations. Let's calculate the predicted activity coefficients. At concentration 0.001 molar, the theory predicts gamma approximately equals 0.966. At 0.01 molar, gamma approximately equals 0.904. At 0.1 molar, gamma approximately equals 0.796. When we compare with experimental measurements, the agreement is excellent at these low concentrations. The theory works beautifully. However, there's an important limitation. The Debye-Hückel limiting law breaks down at higher concentrations. The limiting law is valid only for ionic strengths less than about 0.01 molar. Above this, deviations from the square root law appear. Why does it fail? At higher concentrations, ions get so close together that our approximations break down. We can't treat them as point charges anymore. To extend the theory to higher concentrations, scientists developed the extended Debye-Hückel equation, which adds correction terms for ion size and other effects. Let's dig deeper into the physical meaning. What is the energy associated with this ionic atmosphere? Each ion has lower potential energy than it would in an ideal solution because it's surrounded by oppositely charged ions. The change in free energy per ion is negative E squared kappa divided by 2 epsilon. This is the energy gained from forming the ionic atmosphere. This energy stabilization reduces the chemical potential of the ions, which manifests as an activity coefficient less than 1. The chemical potential mu equals mu0 plus RT natural log of activity, which equals mu0 plus RT natural log of gamma times C. Here's an important question. Why does increasing the concentration make the screening more effective? What's the mechanism? The answer is that more ions in solution means a shorter Debye screening length. The ionic atmosphere becomes more compact and concentrated. With higher ion density, there's a stronger local charge imbalance around each ion. More opposite charges can crowd into the atmosphere. This reduces the effective charge that other ions see at long range, lowering the activity coefficient even more. The Debye-Hückel theory doesn't just explain activity coefficients. It also explains why electrical conductivity deviates from ideal behavior. Ideal solution theory predicts that electrical conductivity should be directly proportional to ion concentration. In reality, conductivity increases more slowly than concentration. This is because ions are less mobile due to their ionic atmospheres. When we plot conductivity versus the square root of concentration, the real behavior deviates from the ideal straight line, curving downward. There are actually two effects that reduce conductivity. The first is called the relaxation effect. When an ion moves in an electric field, its ionic atmosphere can't rearrange instantly to stay centered on the ion. There's a time lag. This creates an asymmetric atmosphere that lags behind the moving ion. The atmosphere exerts a drag force that slows the ion down. At higher concentrations, the ionic atmosphere is stronger and more concentrated, so this drag effect is larger. The second effect is called the electrophoretic effect. The ionic atmosphere, being oppositely charged, moves in the opposite direction to the central ion under the applied electric field. As the atmosphere moves, it drags solvent molecules with it, creating a counterflow that opposes the central ion's motion. The positive ion moves one way, while its negative atmosphere moves the other way, creating opposing flows. The Debye-Hückel theory was a landmark achievement that transformed physical chemistry. This work was so important that it won Peter Debye the 1936 Nobel Prize in Chemistry. It became the foundation for understanding all ionic solutions, from seawater to biological fluids to industrial processes. The theory is still used today in computational chemistry and biochemistry to model electrostatic interactions in complex systems. The ideas have been extended to the Poisson-Boltzmann equation, which handles more complex geometries like proteins and membranes. Let me give you a modern application. The Debye-Hückel theory helps us understand protein stability in different salt solutions. Proteins have many charged amino acids on their surface. These charges interact with ions in solution. The salt concentration affects how proteins fold and how they bind to other molecules. This is crucial for understanding enzyme function. Higher salt concentration means more screening and weaker electrostatic interactions between charged groups on the protein. There are important practical implications for anyone working with ionic solutions in the laboratory. If you're calculating chemical equilibria, you need to use activities, not just concentrations, especially at higher ionic strengths. The pH of buffer solutions depends on ionic strength. A buffer at 0.1 molar ionic strength has a slightly different pH than at 0.01 molar. The solubility of sparingly soluble salts is affected by other ions in solution through the ionic strength effect. At even higher concentrations, another phenomenon becomes important: ion pairing. At high concentrations, oppositely charged ions can form temporary pairs or clusters that behave as neutral species. Ion pairing reduces the effective number of free ions in solution, causing even larger deviations from ideal behavior. The basic Debye-Hückel theory doesn't account for ion pairing. More sophisticated theories like the Debye theory are needed. Let me summarize the revolutionary insights that Debye and Hückel brought to chemistry. First, ions in solution are not independent. They interact through long-range electrostatic forces that create ionic atmospheres. Second, the mysterious square root concentration dependence arises naturally from the physics of electrostatic screening. Third, activity coefficients provide a quantitative way to account for non-ideal behavior in thermodynamic calculations. Fourth, the theory unifies many different experimental observations, including activity coefficients, conductivity, and colligative properties. The single most important equation to remember from this lesson is the Debye-Hückel limiting law. Log base 10 of gamma plus minus equals negative 0.51 times the absolute value of Z plus times Z minus times the square root of ionic strength I. This is for water at 25 degrees Celsius. This simple equation captures the essence of how ionic screening affects solution behavior at low concentrations. The work of Debye and Hückel continues to influence modern science in profound ways. It's used in atmospheric chemistry to model how ions behave in aerosol particles and cloud droplets. It's applied in electrochemistry for designing better batteries and fuel cells, where ionic conductivity is crucial. It's essential for understanding how biological ion channels work in cell membranes, affecting everything from nerve signals to heart function. The Debye-Hückel theory represents a beautiful example of how physics and chemistry unite to solve a fundamental problem. By applying simple physical principles about electrostatic interactions, Debye and Hückel explain complex chemical behavior that had puzzled scientists for decades. The remarkable square root concentration dependence emerges naturally from the statistical mechanics of charged particles in solution. This theory opened the door to truly quantitative solution chemistry and remains a cornerstone of physical chemistry today.